So, good morning, everybody. So, my name is Roland Schnell, the main instructor of this course in wind energy. It's nice to see so many students. This is a very interesting subject, I think. For today, I have two partial lectures. In the first one, I want to introduce the course, what it is about. In the second lecture for today, I will give a brief overview about the subject airborne wind energy, also what you can expect then in the following 11 lectures. But first, let me ask you, who has heard before of airborne wind energy? Is that a subject that you know? Okay, less than half, so then I have the right lecture for you. So first, a bit about the instructors and students, then the learning objectives for the course, structure and resources that I have prepared, and then a few things beyond the course. So, you can later watch this slide presentation online in Brightspace. This is not PowerPoint. I made them with Reveal.js. This is a HTML5 framework that allows you to actually watch the presentation online with all the content that's in, like movies, images, and links to other websites. And here are just some few instructions how to use that. I'm also video recording all my lectures, and we'll put them online next to this presentation, so you have two documented streams that you can use. So about the instructors and the students. So this is my profile. This is basically my career. I have an MSc in mechanical engineering from the University of Karlsruhe, and I did a PhD. I went to ESA at some point, did a postdoctoral fellowship. I worked on the Ariane 5 upper stage engine, very interesting job, then software architect at TNO, finally here associate professor, and I took actually over this subject of airborne wind energy from my predecessor, Hugo Ockels. He was first astronaut, Dutch astronaut in space, and he came up with the subject about the year 2000. I had a few projects here. I'm also in the board of directors of Airborne Wind Europe, which is our industry association. It's a small industry, but we are networked. And we have an IEA wind task. IEA stands for International Energy Agency. Maybe most importantly, I'm also a co-founder of the company Kite Power. That company is located here in Delft, and they are one of the leading companies in this industry worldwide. And I'm sure you will see many of their photos and illustrations also in this lecture. These are my main research areas, of course, airborne wind energy in total, all different aspects. I'm working on this already for 15 years. And computational aeroelasticity and fluid structure interaction. This is my, let's say, specialized area. I have done this also before airborne wind. Everything with free surfaces, interaction of airflow and liquids. That's something I've been doing since my time in Karlsruhe. We have a second instructor, Daniele Ragni, my colleague. He's also an associate professor in our section, and he will jump in if I cannot hold a lecture. We basically nowadays need 2 instructors per course, and he volunteered to do that. His specialities are aeroacoustics, and especially also the noise from aircraft. We are together in a project with Kite Power to investigate the noise emission of the kite when it flies to the ground. So that is all something, I would say, pioneering, like many activities that we are involved in. They're quite early and the first of its kind. This is my research group. We call it the Airborne Wind Energy Research Group. It's a mix of PhD researchers, master's students. We also had here 2 helpers from the Digital Competence Center for the last half year to help us in setting up our software to a high professional standard. I mention software because software is very important in airborne wind energy. It's all about control. We have a free-flying aircraft on a tether, so that's quite different to a wind turbine. We will hear about this in a few minutes, actually. So we need to flight control this, and flight control always involves software, which is why software is the core of the technology, I would say. About the students, we have students from aerodynamics and wind energy, that's the master track. We have sustainable energy technology set. Now we have also a rotor design MSc track from EWAM. And sometimes we have PhD researchers here. Are there any PhD researchers here from graduate school? No? Okay, then not this time. And because the course is followed by students with different backgrounds, I cannot go all the way deep into one specific thing like aerodynamics. So I really need to keep that on a level that it's understandable by everyone. And of course, if you have questions, just interrupt me, right? I have enough time for that. So it's not specialized for a specific engineering discipline, but you do need to be familiar with basic mathematical and physical derivations, which all of you are. Scope and learning objectives. This shouldn't actually be here. We just move it to another slide. The scope about the courses here. So all different words. First I want to look at airborne wind energy conversion concepts, then the key elements of these systems, how do they function. Then of course we have challenges that we need to address, but these challenges also lead us to opportunities. What makes airborne wind energy special? Then I want to talk about the industrial developments, so not only the research here, but also what industry does. The very central thing is the theory of tethered flight. That's something that we have developed over the last, I would say, 15 years in a major way. And that theory is distinctly different to untethered flight. And that has quite a lot of consequences, so that it's actually a theory on its own. The presence of a tether, so this is a kite that is a derivative of a surf kite, leading edge and strut tubes, a canopy. This kite is connected to the ground via bridle lines and a tether to actually transmit the forces to the ground. And by flying, there will be strong forces in this tether. We'll get to that later. And these forces are often a lot higher than the gravitational force that acts on an aircraft in cruising flight. That is at the core of the difference between airborne wind energy, tethered flight, and untethered flight. But we will get to this later. Then performance estimation, that's also quite important. With this theory of tethered flight, how can we actually predict what energy we can produce with such a system? We need to look at the wind resource at higher altitude. Some of you might have heard that when you go higher, that the wind changes distinctly. That is something we will see in this lecture today, and that has quite some consequences. Scaling up in wind parks, that's the view into the future. We are not there yet. We have individual systems that are being manufactured by industry, but we do not have parks, so arrangements of many systems in a wind farm. Also important, economic assessment, environmental footprint. This is a key element of airborne wind energy. Instead of a big turbine with mast, rotor blades, hub, foundation, we have a flying object with a tether to the ground, which leads to huge mass savings and a quite reduced environmental footprint, with consequence to social acceptance. Okay, course learning objectives. And that's now a total view over the next half year. What do we want to learn? You will be able to differentiate the working principles of the airborne wind energy concept. So basically the question, how do we generate energy with airborne wind energy systems? Understand the challenges and opportunities for airborne wind. So why do we do this? Develop an overview of the airborne wind energy sector, and understand why the different companies and academic institutions do this and what are they working on, and identify the so-called TRL, technology readiness level of the different concepts. And I put here a when, because depending on the readiness level, you can expect that a technology will be used. And we are in a stage where we are about to be used in small numbers with this technology. Then, more on a research perspective, you will develop modeling approaches for tethered flight. I mentioned this earlier. Develop operational approaches. So how do we actually fly these kites? What do the kites need to be able to do to harvest energy? Predict the electrical output and identify the design and operational parameters affecting the power output. And lastly, understand the influence of the wind field on the power output. And then I have here the last point, understand how the kite design affects the power output, and also understand the aerodynamics and wing deformation of flexible membrane kites. So these are more understanding subjects, and they will be allocated towards the end of this course, which is I think 9 to 12. This is in the middle part, and this is here in the beginning. Structure and resources. So we have 4 parts. Just mentioned it actually. Part 1 to 3. Introduce airborne wind, present historical perspective on kites, and a portfolio of current prototypes. These will be the first 3 lectures. And the next lecture is actually about the history of kites, kite applications, I should say, which dates back several thousands of years. I will focus on the last 100 years, but still it has a long history. And lectures 4 to 7, they are really I would say the theoretical core of the course. We will develop the theory of tethered flight, and then develop systematically upgrades of that theory that allow us model more and more perspectives of airborne wind energy systems. And we have developed also a self-sustained Jupyter notebook workshop. So this is in Python that allows you to simulate the electricity generation of such systems on the computer. Then in lectures 8 to 9, this is more about the practical operation of such systems in the future energy system. So going from one system to a part. And then here in the last two lectures, more details about the kite itself, the aerodynamics of the kite, structural deformation, and so on. And you know each lecture takes 2 times 45 minutes. That's the schedule for first quarter, lectures 1 to 6. I just put them on here. And there is one lecture here which I keep as a backup date. It's in my timetables. If one of these here needs to be cancelled, then we will shift the whole block down and we will use this 18th of October slot. Then this is the self-paced homework workshop. I will hand this out at some point. And then we have Q2. This block here is the last lecture on 10th of January, and then the exam on the 31st. Are there any questions regarding this layout? Everything clear? And I will, of course, later let you know how I structure this exam. There are I have many example exams placed on Brightspace, which I still need to open, I think. You can really go down through 10 years of exams with an exam sheet and the example solution. That's probably the best worked out documentation of the course so far. So you can actually use this to train for the exam. Here are the resources that you have. That's the Brightspace site. When the texture is blue, it's a link. You can click on that later. Okay, when you see this, you will probably be in Brightspace. You don't really need that. But for other things that are blue, these are links. And you will have, as I explained, the slides and the video. Also, a literature collection is available in the exams. What might be interesting for you is also the book of abstracts of our Airborne Wind Energy Conference. It takes place every 2 years, and it started in 2009, but we really started to document the event in 2011. We have these, 6 books of abstracts. Here there was basically, we were just flying kites, and here we already had first industrial prototypes in operation. You can see the evolution of the technology through these years. Also a little bit illustrated here on the cover page. You can just click on these images and then you get the book of abstracts from the library here. I was lucky enough to be the publisher of all these books, so they are all available from our institutional library here as PDFs. And I have hard copies of these last conferences in my office. If someone really wants to have one, that's also possible. Related activities, maybe this is a bit too detailed, but I mentioned it already. We have an industry association, Airborne Wind Europe, since 2019, and we have this IEA Wind task. These are measures that helped us in the last 5 years to really go from individual companies and research groups that just wrote their own things towards a networked industry and academic collaboration. So with these 2 activities, we coordinate everything. We have regular meetings. We set up common working groups, for example, one on environmental aspects, where we look at the impact with birds, bats, and so on. How do these kites affect these? We look at safety, regulations. These are topics that are of interest for all companies. So it's good to have a central place that takes charge. So they're basically bundling resources. If you're interested, we have social media presence here, also a YouTube channel, which is called Laddermill. On this are many videos from conferences, from tests over the last 15 years. Maybe most interesting is this piece here. That's a documentary movie. That's actually the cover page here. When you open it on the internet, it's called, maybe I should write that down, I forgot here. If you go to McCartneyFilm.com, you will see this page, and it's actually a documentary about the quest of this company, McCartney, from 2006 until 2000, to develop the largest energy kite in the world, a 600 kilowatt single wing, 30-meter wingspan kite, and they demonstrated this in Norway, offshore, flying from Spark. This is an impressive technology demonstrator. It was a Google moonshot project until 2000. Google shut it down because they lost interest in this energy technology and had to save also some money. It's expensive, obviously. But they opened up all the 400 patents that they developed over the years for this technology. And they opened up all the documentation, all the software, all freely available. And they sponsored 3 filmmakers to actually create and assemble this movie from footage that they had taken over the years. It's a very nice feature film, 1.5 hours. It's on YouTube. When you go to this site, it will actually, let me show you. It doesn't scroll down, you just have to scroll down, and you can watch the film here. It has also a bit of documentation and also some links to the filmmakers. Okay, that's a recommendation. Beyond the course, a few things you might be interested in. We have quite good connections to industry and to other academic research groups. If you are interested in internships or in graduation projects, please contact me. There is always a few available here at these industries, and a bit less internships, at least with academia. But I can connect you. I know most of the people working here, and they always ask me, do you have students who are interested to do something with us? We will anyway later see what these people here are doing, so I will not go deeper into these names. And that is something specific for this year now. We won a EU-funded doctoral training network this year. The training network is a Marie Curie action in the Horizon Europe framework program. We have these partner institutions here. DTU is the coordinator. We are partners. So you see we have 4 universities and 4 companies. Airborne Wind Europe is an association. Project starts December this year. We will hire the first 12, we will hire the 12 PhD candidates in this time frame here, April to June, which might be something for you if you find this course here interesting, of course. These are the 12 topics we will be hiring. Here at the back in brackets I put the institution. The first one is always the hiring institution. And if there is a second one, like here, this is for academic supervision. So especially for the companies or actually only for the companies. There must be an academic supervisor. You will get the PhD then from this university. So there are all 12, I think, quite challenging and interesting subjects. If you're interested, maybe this is more towards the end of the course. But of course, we try to find already now good candidates. So it's actually good to keep an eye on that. Okay, so far for the quick introduction to the course. Are there any questions? No? And let me head over to the real content. The introduction. I have here only two subjects. So first the learning objectives and then airborne wind energy. Learning objectives. This is a bit the repetition from what you saw before. So in this specific part, I want to look at the different working principles of airborne wind energy and make you aware of the challenges and the opportunities of technology. It's basically a very rough outline of what this is about. I also put here literature. This is a book chapter. If you click here, you should get actually, you get to the list of references in the end, and you see here the book. You can go to this DOI link, click it, and then it brings you to the book chapter. I will also make this available in your on Brightspace. Actually, here this hamburger symbol is the. If you later need to operate this, you can move around in this presentation. Okay, so you have the literature chapter here. So airborne wind energy, what is it? Here we have a conventional horizontal axis wind turbine. Wind comes from the left, and as you all know, at the ground the wind is zero because we have a boundary layer flow. Then with height it typically increases. It does increase, there is wind. How it will increase we will see later. But with this wind, the turbine can generate energy, and the conventional wind energy, you all know that, has rotor blades. These rotor blades move in the flow, actually perpendicular to the incoming wind, ideally. You have a generator here on the hub of a tower, and by the rotation of these blades, the generator produces energy, goes down the tower into the grid. That's how a horizontal wind turbine works. What's specific here is the motion of the blades are constrained. This entire rotor can just rotate around the hub. So, and that mechanical constraint requires quite a lot of mass and structure. You need a tower, you need a quite good nacelle, you need rotor blades that are very strong at the base, and the tower needs to go into a foundation which is quite massive. Because, see, when the wind comes, there will be a thrust acting on the turbine nacelle, and this thrust will create an overturning moment, and that needs to be actually with the foundation needs to withstand that. And all these forces and moments lead to a quite large installation. The advantages of this concept, these mechanical constraints allow the rotor only to rotate, and you don't need advanced control techniques. For this reason, of course, wind turbines exist already for a very long time and have been used for many purposes. So what is airborne wind? In airborne wind, as I explained, we replace the tower by a tether. A tether is a flexible cable. 100 years ago, the kite tethers were made of piano wire, so very thin steel wire. But since then, technology advanced, and nowadays we use plastic wires. It's not regular plastic, it's high-performance plastic material. One brand that has been used is Dyneema. Dyneema is unidirectional polyethylene molecules that are combined stronger than steel. So with these plastic tether or Dyneema tethers, the kite is actually anchored to the ground. And here you see something that we call an airborne wind turbine, where a kite, which is this main wing here, and the tail wing, carries onboard wind turbines. So how does that work? Similar to the horizontal axis wind turbines, the main wing creates lift and drag forces, aerodynamic lift and drag forces, and we will later see how exactly that works. With these forces, the wing is moving forward. It's propelled forward. So this wing will fly because it's anchored to the ground. Actually, the incoming wind will be a relative airflow, and the wing will move around. That's exactly the same principle, 100% the same principle as the rotor blades move around the hub. The only difference is that here we use a tether to hold the kite, and here we use a tower cell to hold the rotor. But with this arrangement, tether and wing only, the tail is only used for steering. With this arrangement, you cannot produce energy. Right? The wing would fly on circles, let's say, or however you steer it, also figure eights or other flight patterns, but you cannot produce energy. So what the trick is actually to mount onboard wind turbines. These onboard wind turbines, they see a much higher wind speed on the flying kite than as if they would be mounted here statically at the ground. So actually we use the wing in this setup to create a high flight speed, and that high flight speed creates a high relative airflow acting on the kite, and that high relative airflow can then be harvested with these small wind turbines. That's why we call it airborne wind turbine. I use the word relative airflow. Is that something familiar to you, relative airflow? I give you a mathematical definition here because we will use this over and over again. Just write that down first. This is what we call an apparent wind speed. And every sailor among you will know this, called better velocity. This here is the wind velocity, and this one is the kite velocity. So the apparent wind velocity, which is actually synonym to relative flow velocity, the apparent wind velocity is the wind velocity minus the kite velocity. This is a very standard definition of a flow velocity, a relative flow velocity acting on a moving object. And the moving object is the kite, And this V wind is the ambient flow velocity. So basic physics. And this is the effect that these onboard wind turbines here exploit, because this wind speed is normally, maybe I give you a number example, then it's clear. The wind speed typically is around 5 to 10 meters per second. With a fast flying kite, you can achieve kite speeds of, let's say, 30 to 50 meters per second. You can see this is a vector equation, I should say. So these are really vectors. These are the magnitudes of these vectors, but you can already see that even for a lower wind speed with a high kite speed, create a much higher apparent wind speed. That's the underlying principle that is exploited here. With the rotor of a wind turbine in an airflow in a wind, you get very high speeds here, typically only at the tip. But the tip of the rotor is a small part of the whole installation. With an airborne wind turbine, you have this high speed everywhere on these small rotors, because this wing, free-flying wing, acts like the wingtip on a wind turbine. Just for you to visualize. So we'll have a break in 5 minutes. And then next I want to go to another concept, that the so-called pumping airborne wind energy system. Why pumping? Because we have two phases. We have a reel out phase where the kite pulls the tether from a drum, and a reel in phase where the drum pulls the tether back, and with the tether also the kite. The drum here is connected to a generator. You would call this also a winch. This is typically a winch setup, generator, electric generator that can also be operated as a motor, like in an electric car, and a drum. The drum converts a linear force from the tether into a torque. The torque acts on the axis. So when the kite reels up, when the tether is reeled out, what do? We fly the kite in these figure-8 maneuvers. Very fast crosswind maneuvers, like that. It can also be circles or figure-8s. I will have some illustration later why this is important. When you fly crosswind, the tether force is amplified dramatically. And that is something that we will analyze also theoretically in later lectures, exactly how much. Then to fly back, we stop these maneuvers. We basically park the kite into the air. We stop it from moving. You see it already from this equation that between reel out with crosswind maneuvers, fast flying crosswind maneuvers, and reel in with this kite velocity dropping to just the reel-in speed, makes a big difference on this VA. And maybe one additional formula to start. This VA has an important effect on the aerodynamic forces. Let me write this down. 1/2 rho. I just need to get that right first time. CR is VA squared. Let me tell you one more thing. When I put an arrow above a variable, then it's a vector. Got to say that without the arrow, it's the magnitude of the vector. So this is really just a scalar equation. So you see here this VA enters a term for the aerodynamic force with a square. So the relative velocity, the magnitude of the relative velocity has a big impact on the aerodynamic force. So I would say this equation here and this equation are quite important for this course. This FA, the aerodynamic force, in a first approximation is quite similar to the tether force that acts on the cable. So you see that with the flight speed of the kite, you can control the force in the cable. Because of what I explained now, the force during reel out is a lot higher than during reel in, because we stop the motion of the kite. We do one additional thing, which I forgot to mention, is we depower the kite additionally. We rotate it, we pitch it down. And you see this here a bit illustrated. When you pitch down a wing, you decrease the angle of attack. And decreasing angle of attack will vary this coefficient here, this aerodynamic resultant coefficient. So the force here is lower than during reel out. And because, let's see if I illustrated this now, because I have a higher force during reel out than during reel in, we have a net energy over such a pumping cycle. What I forgot to illustrate here is we always need a storage, typically electrical storage, like a rechargeable battery, that can store the energy from the reel out and feed back a bit of a fraction of that energy to reel back in the kite by using this generator as a motor. So that's why it's called pumping cycle. It has, it's similar to some degree to a piston engine. In a piston engine, you have also a cycle. You have a combustion stroke, which generates energy, and you have a compression stroke, where energy is used, and the energy is stored in the kinetic energy of the crankshaft. Crankshaft equalizes the cyclic operation, and in our system we use a rechargeable battery. Because we rushed here a little bit at the end, and it's quite important to understand this basic working principle. Are there any questions regarding this? Is it clear the difference between the airborne wind turbine and the turbine itself? Then this generation principle with the generator on the ground, and the reel out generation and reel in consumption phase. Is that clear? Yes.
For the airborne wind turbine, so the last one, how do you store the energy from the turbines?
Mm-hmm. There is something missing here. Indeed, the electricity is generated on board, and it's then conducted down to the ground. For this concept, there is no storage needed, because once it's flying, like with the wind turbine, the electricity can directly be used. There is a network, of course, where it's feeding in. So the intermediate, the storage is only required for this concept where we have an alternating generation and consumption phase. If that would be connected to the network, you could also use the network for this, but an electricity network does not like to be fed with energy and taken out in cyclic operation. The grid operator will ask you to have a constant input. So for that reason, we use a battery to store the cycle, let's say, excess, to only use the cycle excess and keep the small part for the retention.
Yeah, makes sense. I also have another question for the Not the turbine now. Yes, for the kite. So you mentioned that you can control the pitch with the tethers.
Yeah.
But how do you? Where is this like motor? Like, is it stationed on the ground? Is it stationed in that little separation point?
Excellent question. I also was too fast here. In this concept that you see here, we have one tether, and the tether links to this little box. This little box is a cable robot. It has two small motors inside. I have that thing in my office. I will bring it in one of the next lectures. And with these two motors, it operates on the tethers and can actually, like a kite boarder, can steer the kite or change the pitch of the kite. There are other concepts where all 4 lines or 3 lines come to the ground, and you have these motors here on the ground. But that depends on the concept. I didn't want to distinguish here, but you're right. The steering and control is really done by this box. And it's connected to the ground, not through the tether, but through wireless signal. The difference between the turbine, the airborne wind turbine, and this concept is that here you need a conducting tether always, because energy is generated on the kite, and here you need you only need a connection to control this box. If you keep this box on the ground and have multiple lines going to the kite for control, then you don't need anything on the kite. This is the most lightweight version, because every mass like this weighs. Let us continue here and we go there.
Yeah, what happens when there's no wind?
When there is no wind, we can start here. This will just stop turning. This can continue flying if you reverse the energy and pump into the kite, because then you can use the turbines as propellers and fly. You can do this for a time when there is only a small dip in the wind. Then it's actually quite useful to avoid a landing, because landing and relaunching is always tricky and more dangerous. With this concept here is more complex, depends a bit on the kite. With the soft guide, they are lightweight. You can try to fly higher, and because the wind speed typically increases, and you might catch a higher wind speed all the way up, and you can park the kite, at least that. And then you come down when there is again more wind. It's very important for these concepts that you know exactly what the wind speed is where, because you can optimize the operation, because you can reel out more or less, and by that adjust the operation of the kite. You can't do that with the wind turbine.
How much does the tethers and the interaction with the air influence the performance of
the tethers have quite some impact, because they go just here, they induce drag. Like also the kite has drag, aerodynamic drag, and the more drag you add, I already erased it, the slower the kite will fly, obviously. We'll get to the theory later. When the kite flies slower, you saw from this formula, the apparent wind speed gets lower and the performance will drop. So drag is always negative.
I mean more in terms of how large is the percentage?
Oh, the percentage.
Undisturbed, like inflow.
When the tether is short, the percentage is very small. Let's say if you have a tether of 100 to 200 meters, you probably have 10% drag contribution from the tether. Depends also on the size of this installation. For large kites, I think the tether drag decreases relative to all drag.
And then also, it's like for the kite itself, it also like not only the tether like to the kite itself, but also like with the controlling of the like the control tethers.
You
How
mean
much do they?
we call them bridle lines, but they are controlled tethers. Yeah, they also exert drag. Just to give you an example, this kite here is a 25 square meter kite. That's the wing surface area. All the lines that go down to the control unit, they are in total 100 meter long. So when you add all these line elements together, you have 100 meter of extra line, but they are much thinner and have lower drag than this main tether. This main tether is now 8 millimeter, 1 centimeter. There was also one question in the back. I think you wanted to ask something, right? No? Colleague? No? Okay. Any other?
I mean, maybe this is a bit far-fetched, but how heavy is a typical kite? Like,
Depends on the size. This system that you see here, 25 square meter, that's the TU Delft kite that we built in 2010. That weighs 20 kilogram. Already our spin-off now with the 60 square meter kite goes to 70 kilogram, but that includes also the control unit. The control unit now is already a small, I would say, an aircraft in itself, with a lot of padding, but still. You could say half of the weight is in the wing, half of the weight is in the control unit. You have to imagine such a kite like an aircraft with a fuselage and the wing separated by these bridle lines. And the trick is to, the trick is that this wing here is inflatable, meaning you can pack it very small, and it's actually kept in shape by the aerodynamic suction pressure. So when it flies, there is a suction pressure here on the upper canopy that pulls it in shape against the restraint of the bridle lines that connect it to this control unit. This is how it works. Have another question?
Yeah, also, I mean, okay. It's kind of a weird question, but is there a balance in between like how far you stretch it and like, because the more you stretch it, the more mass you're gonna incur, right?
Absolutely.
So there should be a balance between how much you stretch it and then deciding, okay, you know what, let's reel it in and then pull it back out again. Is there some kind of technique to say, okay, it's time to reel it in so we don't have this much mass from the tether, and reel it back out?
This is a core optimization issue in our field, to determine exactly what's the minimum tether length we need. And normally this is a pure safety constraint. You want to have a certain distance from the ground. So we have a kind of a Z-min that we need to maintain. There we can, depending on the elevation angle, that gives a tether length then. And then we have a maximum tether length that comes from the whatever tether we have on the drum. And there is an optimum how much you reel out. And because was asked earlier, the longer the tether gets, the higher the drag will become, the higher the impact on the performance. On the other hand, flying higher sometimes gives you more wind speed because the wind profile, the wind speed increases. So this is really a trade-off problem where you need to look at the instantaneous wind profile, how much tether you have. You need to take into account that each pumping cycle takes about 3 minutes. So you cannot instantaneously optimize. You need to have like an optimization over these pumping cycles and have a good prediction of how the wind develops. another
What is
question.
like the first place where this is going to be applied? Is this first going to be offshore, for example, or is this first in like more remote areas, or
Yeah.
like starting to with the minima you said, like with 200 meters and stuff?
Yeah.
That already sounds a bit like you can already put it in like more urban areas.
Yes. Also depends. Makani Power, with the documentary, they decidedly went offshore. But that has had the reason, I use actually their Wind 7 prototype here, that has the reason that these wind turbines, you can imagine, they are like sirens. They are very loud. Although they put a lot of effort into reducing the noise emissions of these turbines, it was clear that they will probably have to operate offshore, where sound does not matter. So that's why they really went strategically offshore, and they also demonstrated the operation offshore. For these kind of systems, they can also fly onshore. And the reason to fly onshore is, of course, simplicity. To bring this equipment offshore makes everything much more complex. Not only because the installation can move, let's say on a floating platform, so you have the additional motion, but also you need to bring things offshore. Everything needs to be corrosion proof, needs to be seawater proof, and you cannot easily go there. You need a ship. So I expect that first deployments will be onshore.
Then generally, like the air disturbance is more predictable.
Is more predictable, exactly. And I say I predict. I should actually correct myself. We are already a bit further. The first deployments are onshore. So Sky Sales, which is market leader, has already 2 or 3 systems sold. One is in northern Germany, one is on the island of Mauritius. Kite Power had an installation on Aruba. It's now operating in Ireland. Maybe I should show you. They just had a video. Let me see if I find this. I think it's pretty nice. See the kite flying? So that's that test site in Bangor, Eris. That's on the northwest coast of Ireland. This is the ground station. You see the tether. This is the swivel point. You see they have no foundation. This is a peat field, so it's actually swamp. They just needed to put gravel here. I can make this a bit louder. No, I can't. You see the control unit. This black dot here in the front here is actually a sensor box. You see they fly very close to the ground, maybe 100-meter tether length.
It would generally be, because like one every few thousand kilometers is probably not what is desired in the future to accompany like all the energy change and transition we want to accomplish. But what would be the distance like from these stations?
Oh, you mean from each other?
Yeah. What is possible?
What we normally do is we have the ground station at the center, and you take the maximum tether length, and then you draw a circle. This is a super conservative estimate. We have already in studies determined that you can move them much closer together, because you will never have one kite for some reason all the way upwind flying. That's almost not possible. And the other one all the way downwind. So they will all synchronize with wind speed. It's going a little bit too much into detail, but you can stack them with the tether length apart.
Also control, of course.
Exactly, and you could synchronize the control. So for control engineers, this is a favorite subject. And it's also why airborne wind, one reason why airborne wind energy came into play. It was rediscovered by control engineers, and then they developed the theories for this, and later industry picked up and found this also a very good application. Okay, let me move back. Any other question? Yes, here.
Are there any tries on the bridle line, at least, to have a cushion so the drag is reduced? Instead of a circle, right? The drag is quite high in a circle.
Ah, you mean the cross section of the tether?
Yes, yes. I mean, on the tether, I can imagine it's a bit difficult because you have to stack it on a drum.
Exactly.
But on the bridle.
Bridle here,
On the
yes.
bridle,
Yes, yeah, you could say, and you are partially right, the reel out and reel in typically happens only to a certain length, because the upper part of the tether is normally not reeled onto the drum. The kite rarely locks. At least for kite power, we don't have a launch mast. We have a winch launch, so there is a part of the tether that's free. We have researched this at the university 10 years ago. It's interesting, but it's not a core issue that we have. It's one of the little improvement areas that you could tap into once everything is deployed, customers buy it, we want to improve the technology further, then we will probably see aerodynamically shaped bridle lines and things like that. But so far we are in the stage where we try to prove economic feasibility. We have shown, economic viability. We have shown technical feasibility because we have deployed these systems. They work as they should, but we need to now show that they can also produce revenue in competition with wind turbines. And that's tricky because they're already quite cheap in the meantime. Any other questions? Otherwise, we continue. That doesn't look good. Sorry. Let's see that. Okay. Maybe this is just a summary what airborne wind energy is. I mean, this is basically what we discuss now. Maybe most interesting is this link here, awesco.eu. And then Airborne Wind Energy explained. AWESCO is the name of the EU doctoral network that I coordinated some years ago. And this is a very nice introductory article, a bit like a blog post, explaining the technology, a bit the history and so on. Have a look at that if you want to kickstart your knowledge. And that's a quote from that website. So what are kites? I have already shown you this leading edge inflatable kite, which you see here on the left. But there are many more types. We have also this C. So maybe before I do this, this is so-called bow kite. Are there any kite surfers here? Okay, yes, super. Then you know. Correct me if I'm wrong. I'm not a kite surfer, but I learned this in theory. So, bow kite means the leading edge is shaped like a bow. You see this here also in the image. You have power lines that connect, so these are the two power lines that connect via bridle to the leading edge. So, with such an inflatable wing, this is very deformable. Without the bridle lines, you could not maintain the shape of this wing. So the bridle lines are structurally very important. The power lines connect to the leading edge, and they carry most of the load of the wing transmitted to the ground. Then you have the steering lines, and they connect more to the tip areas in the back. With these steering lines, you can pull the tips or release both tips together and depower the wing. So this bow kite design is quite young, relatively, and it's used in kiteboarding, and we have adopted this in many airborne wind energy concepts. The sea kite is a bit older, and you see a bit like 6 years. It uses the same construction principle, the leading edge tube and the strut tubes, but it has here these 4 lines, 2 power lines in the front coming from the tip, and these rear lines here attaching to the tip. It uses the same principle for steering. Then we have this special foil kite here by Sky Sails. It's a large ram air wing, and ram air, I explain in the next slide, uses the stagnation pressure from the relative flow to inflate this wing. So I forgot to mention these tubes here in these 2 designs are pre-inflated. I've seen this sometimes at the beach. Kiteboarders carry their kite there, and that they start to pump air into these tubes. The tubes are all connected, and in the end you have a relatively stable wing shape. That's also one advantage of these 2 wing types, that you have a wing that looks like that. You can put it on the back and you can launch it with your bridle system. A ram air wing is just a piece of cloth without any pre-inflatable elements. You really need to get this thing flying somehow so that the wing, the stagnation pressure inflates the wing. Here are actually the openings for the incoming air for the stagnation pressure to inflate. Sky Sails used this design with only 2 tip tethers because the entire wing was steered by roll control. Goes a little bit too far, but since I'm already talking about it, the bow kite also twists the wing, and in this way creates a steering moment. Also the sea kite does that, but the Sky Sails kite just rolls the entire wing with these 2 lines, and in this way rolls the lift vector. Then we have the typical tethered aircraft. So there's just a regular aircraft with 1 tether connected to the airframe. It's the MPX design. Then we have the swept fixed wing, Enerkite design. Enerkite speciality is that they have 3 tethers that run all the way to the ground, and they have 3 winches on the ground that then control this wing. Power line and steering lines. They claim they have the most lightweight design because there is nothing heavy on the kite, no control. It's just an aerodynamic surface with bridle and tether lines to connect to the ground. And a lightweight wing gives you the advantage that you can fly it at very low wind speeds. With this kite and the control unit, you need a bit higher wind speeds. And then we have this segmented sea kite that is already not operational anymore. So, these were 3D views. Now we look in 2D, what's special about these kites. That's the LEI, leading edge inflatable kite. It's basically a cut through the wing here, or any other span station. You see here the tube and the canopy. The airflow typically has here this recirculation zone. Other than a closed wing profile, the flow separates here, even at low angles of attack, and creates a recirculation zone, which is giving us a hard time when we try to solve the aerodynamics. So if you try to use X-foil or tools like that, That's more difficult here because you deal with separated flow. At higher angle of attack, you also get separation here from the trailing edge. So I mentioned the ram air wing. It looks like this. It's basically an air mattress, you have to imagine, with an opening in the front, and the incoming air creates a stagnation pressure, and that stagnation pressure is active in the whole inner volume, and that the shape of this wing is defined by ribs that are actually defining the airfoil shape and keeping the two skins, the upper and the lower skin, in shape. Because in between the ribs you have, of course, just the canopy. These kites will balloon very strongly. Also, this type of wing balloons, with ballooning, it's a special kiteboarder term. With ballooning, I mean the canopy in between the struts, which actually provide the support, will balloon a little bit out. So in flight, the canopy does not look like this, but has these bulges here. You will see this later in photos very clearly. Then we have the single skin kites. They were not among the ones that I just showed. In the single skin kites, designers entirely skipped the leading edge. I think they even skipped also the struts, and they actually took over the function of the leading edge and the struts purely by bridle lines that actually transmit the force. And only this shape here, you cannot do that with bridle lines. For this shape, they used rigid stiffeners, so inserts, plastic, metal, that form the typical nose profile of a wing. But these were the only rigid structures in such a single skin kite, and the rest is just canopy and bridle lines. This is the very lightweight kite design. It's used for snow kiting. I have seen it. Not so much on the water, I believe, because the advantage here is this swims when it falls on the water, and this does not have any inflatable area. So we have also used this for our concept some years ago. And then there is a special concept, the rotating balloon kite. It sounds quite fancy. It uses the so-called Magnus effect. Who knows what the Magnus effect is? Okay, not many. So if you have a cylinder, and the cylinder is in an airflow, and the cylinder rotates, this cylinder creates a lift force. If the cylinder does not rotate, if you take this piece of chalk, in an airflow it would not create a lift force. But if it does rotate, it creates a lift force. That's an aerodynamic effect, actually an implicit aerodynamic effect, and it's called Magnus effect. Magnus. And that has been used also for, or it's actually used for ship sailing. It has been rediscovered. It was already used in the 1920s on some experimental boats. So large cylinders that are actually on the boat deck, and they rotate. They create very large lift forces. It has been rediscovered. It is mounted already also on ships and used for wind-assisted ship propulsion. And that uses the Magnus effect. And there have been concepts that also use, and still are, that use this for as a kite. The advantage is the lift force is very high that you can create, but it's also more complex. About control, kite control, I mentioned already In the typical kite, you have power lines and steering lines, and you use the roll of the wing and or the twist deformation of the wing. So twist deformation, I mean a spanwise twist like this. Roll would be this. Now this is yaw, and this is pitch. So via the bridle lines here from the ground, or you have a suspended control unit. This is here the standstill swing. And maybe here I have one slide on why do kites fly, but I think we explained this already. A kite flies because the anchoring to the ground creates a relative flow velocity. Without this anchoring to the ground, the kite would just float along with the airflow and would naturally sink to the ground because it's heavy. But because it's anchored to the ground, it cannot move with the air. There is a relative airflow because it's aerodynamically shaped. It creates aerodynamic lift and drag forces. That's how a kite flies. A glider aircraft is not tethered. It uses the gravity to create a relative velocity. Because of gravity, the glider aircraft sinks, and already the sinking motion creates a lift force and drag force, and from that it gets a forward force, and in this way starts gliding. We will use gliding, the theory of gliding, actually as an onset to develop the theory of tethered flight. It's an interesting analogy. Powered aircraft require a propulsion system to create relative velocity. And with this you have most freedom, of course, because you're not depending on gravity, wind, or the tethering, so you have your own propulsion system. There are kites with own propulsion system where this is all combined into one. And balloons, of course, use aerostatic lift. And here I call this the power of crosswind. This was an experiment of my students on the beach with a small 1 square meter kite. And crosswind motion, that's the essence of airborne wind, means when you fly perpendicular to the wind in these maneuvers. You see here already that once you start flying these maneuvers, the kite pulls much harder than when you just statically hold the kite. And that's the essence. So here, this again. So here, pilot just holds the kite still. It pulls very little. In fact, only the wind velocity acts on the kite. Now once you start flying, you have this relative wind velocity formula. And then the kite starts to really pull hard. That's the difference between the reel out phase now, although pilot cannot reel out, but at least it's pulled, and the reel in phase when you start to keep the kites, when you try to keep the kite steady. And that this alternation between crosswind and no crosswind, that's what we use in the pumping kite concept. And here it's again just illustrated what crosswind is. Basically that's the wind velocity, that's the ground station, the kite. And typically we fly these figure-of-8 maneuvers or circular maneuvers to have this crosswind motion. Maybe one slide about terminology, because I now call this airborne wind energy, but there have been other terms in use. You will find in older literature airborne wind power. You will also find kite power, high altitude wind energy, high altitude wind power. They have all gotten a bit out of fashion, and nowadays we call it airborne wind energy, also to have one single term. But if you read old literature, you might come across these. one slide about the analogies between the horizontal axis wind turbine and airborne wind energy systems. You see here, for example, we have the tether, we have the tower, the platform. So actually it's built up like this: ground, then platform, tower, then the nacelle generator, here the drum and the generator. Then you have the rotor blade and the kite, and the hub itself is the drum, where basically the torque is generated. That's the analogy. The difference is a lot less mass. Instead of mass, we need software, sensors, all these things to control the flight of the kite. And that's the challenge. Without robust and reliable control, there will be no commercial viability of airborne wind. I think that's clear, because if you crash too often, you cannot produce energy reliably, and you will not have any success in deploying this. And I put this here on one slide. Here on the left, the opportunities, here the challenges, but let me start with the challenges. Airborne wind is more complex than wind turbines. A wind turbine is a relatively simple construction, right? 1 degree of freedom, heavy materials, can only rotate. I say simple. Nowadays turbines are also complex, but just from a concept point of view. Airborne wind requires reliable and robust control. We depend on high performance materials. You see here this plastic tether, the canopy of the kite, also plastic. You can imagine that with UV and all the environment pulling on this, this will deteriorate over time. So less mass actually requires high performance materials. And this is a key point: how often do we have to replace tether and wing, and what kind of impact does that have on the economics? And we need to revise the current regulatory framework, because we do fly in airspace. Luckily, here for this last point, it's quite a complex point, there is a new drone regulation now in place, which allows us to position airborne wind quite well and provides all the means actually to operate, or to also plan for longer term operation. So these are the challenges, but for this we get opportunities: less material, highly adjustable to the wind resource. That second point is very important, because I mentioned earlier, we can fly higher or lower wherever the wind is stronger, or when the wind is too strong, we can also avoid the strong wind and go lower.
Is research already done on making kites from recycled material and stuff, and incorporating that into the company?
My last graduation project with the student was exactly about that. I have this open here on my laptop, but I'm afraid this will not be enough for this introductory lecture. Interesting thing is, we do something that is called a life cycle analysis. For fixed wing kites and for soft wing kites, we compare it to wind turbines, and there are quite a lot of advantages here, especially on this material aspect and on criteria like global warming potential and cumulative energy demand. These are two metrics that are very important. We see that although the mass goes down drastically for such a system, the environmental impact is not equally lower, because the high performance materials are still much more polluting. But still, there is an advantage. So recycling is something that we investigated and that helps. If you have heather and kites that you can recycle and you can partially at least bring back into the process, this would be a key argument. Access to higher altitude wind, I mentioned already, and what I haven't mentioned is the increased mobility. If you have a lightweight system that only consists of the generator, goes the kite, especially when it's a soft wing kite that fits into a bag, and you can just slide it in here next to it. If you only have this, you can imagine you just transport this somewhere or throw it off an aircraft and immediately you have energy. You cannot do this with a big turbine, even not with a small turbine. So the reduced mass argument has a big impact on the mobility. Are there any other questions, especially about this? I have more details on this, but I think we need to move this to other lectures. Let me just check. Maybe, no, I think if there are no questions, we stop here.